Smart. Better. You have to see. Okay. So we are done with the fifth chapter, right? So we are starting with the new chapter, so you have to understand. Any help needed? So the next chapter that we are going to discuss is called as electromagnetic induction. The sixth chapter is electromagnetic induction, or we call it as EMI. Okay, write down the heading. So write down the heading as electromagnetic induction, or the bracket write it as EMI. So let us first discuss the logic of how things were invented, the order in which they were invented. So first, we came to know the fact that current carrying conductors produce magnetic field. So if you look at the basics, right, you know that charges create electric field. So charges which are at rest or in motion create electric field. When the charges are put into motion, in addition to the electric field, there is also magnetic field that is going to exist. So to conclude the whole story, can we say that current and magnetism are related parameters? When I say current, it is about electric current. So electric current and magnetism are related parameters, right? Now an important question that arises is the reverse process possible? In the sense, when you can use current to generate magnetism, can we think of using magnetism to generate electric current? So that was the next question that was asked. Right? When you think of the fact, we know that nature is symmetrical. When A gives you B, then B can also give you A. That's what they believe in. So electricity can generate magnetism, and magnetism can generate electricity. And this chapter is all about the reverse process of using magnetism to induce electricity. That is why if you see the name of the chapter, electro refers to charges. Magnetic refers to magnetism. Induction refers to creating something without any physical contact. So we didn't say electromagnetic touching what we do. So electromagnetic through the process of contact, or electromagnetic friction, something like that. We never use such words. So it is all about inducing something. Inducing means generally you induce something without a physical contact. Okay. For that, let us see a small simulation. Suppose I have a coil like this. By the way, those who are online are able to see the screen.
Yes, sir.
Yes, sir. Yes, sir.
Listen to this carefully. Okay? Suppose I have a conductor which is formed in the form of some shape. So here when I say conductor, I need to first ensure that I have a loop. So when I say loop, loop is a closed structure. So I have a closed structure here where a bulb is connected to the coil for the purpose of testing. And what do we have outside? You have a magnet. Right? Now see, you tell me what do you think will happen when this magnet is moved within or outside this coil? Concentrate, these blue color dots are actually electrons. Okay, so when I take this magnet and try to push it like this, are you able to see what has happened? Did you see what happened? What happened to the bulb? Observe the bulb. So I move the magnet. The process is little slow because of internet. Okay, so all these things are running through internet recently. So when I move this magnet, inside and outside, I'm able to observe that the bulb is glowing, but it is not glowing continuously. That is a different story, but it is glowing. Right. Here comes an important question. How is it able to glow? So what is making the charged particles go into motion? So for that, the important observation that was done by Faraday, okay, where he told that if you are able to change certain magnetic parameters, you can induce EMF. So when I say inducing EMF induced will always cause the charges to go in a motion. Are you in acceptance with this? Okay. So from this, you are able to understand that when a magnet is moved towards a coil, I repeat it again, this will not happen with an open conductor. When you move a magnet towards a coil, you can observe that electricity is generated. Is the point clear? Now I have another question. Is it always necessary that I need to move only the magnet towards the coil, or can I think of moving the coil towards the magnet also? I can do the reverse process also. When I do this, what is happening? Again, I'm able to see a glow in the bulb. Is it clear? With this observation, we are going to frame a theory of what exactly is the reason behind all these things to happen. Right? So, should we get started? As I mentioned, we have something called as electromagnetic induction. Electro refers to charges, magnetic refers to magnetism, refers to magnetic field, and induction refers to the process of generating something without a physical contact. So generation of something without a physical contact. Okay, when that is the scenario, first thing is, when I try to move the magnet towards the coil, there is a certain parameter or a certain magnetic value that was associated with which I changed. What is that value? Any idea? It's called magnetic flux, and it is represented with the symbol phi with a B around. So B as a subscript. So what does magnetic flux refer to? It is the number of magnetic field lines that are passing through a given area perpendicular, normal. So write it down. Number of magnetic field lines. Number of magnetic field lines passing through a given area. Passing through a given area perpendicular to it. Okay. So how do you write the mathematical formula? Suppose I have a coil like this and the magnetic flux is in this way. Right? I want to write the formula for it where I call this as the area vector. Area vector is generally a vector which is perpendicular to the coil, right? And it is normally in the outward direction. So when I take this, if this angle is taken as theta, then how do you write the magnetic flux as? You can write it as BA cos theta, or this can be written as B vector dot A vector. Is it clear? Now, what is going to be the SI unit for it? SI unit for magnetic flux. So, magnetic field is measured in terms of Tesla, and area is measured in terms of meter square. So, this Tesla meter square put together is given a name called as Weber, and it is represented by the symbol capital W and small v. That is why when you see the previous chapter, some of the places they have told you Tesla is also equal to Weber per meter square. You see some of the problems for magnetic induction they have told the value of magnetic field is Weber per meter square. That is also called as Tesla. So yeah. Now, since we know what is magnetic flux, right? We will be able to try to understand Faraday's law of electromagnetic induction. Can we try it? So Faraday's law of EMF. Any idea? Now, to recollect the simulation that we saw, what did we do? We had a coil, and across that coil, you moved a magnet. When you move the magnet, can I say that the north pole of the magnet, when you try to take closer to the coil, did you try increasing flux or decreasing flux? You increase the flux. How did you say increasing? Because magnetic strength is maximum near the poles. So when the coil is there, when you move the magnet closer to the coil, you observe that the magnetic flux increases. When you try to move it away, you observe that magnetic flux decreases. But here, one thing is constant, that the change in magnetic flux is always taking place when there is a relative motion existing between the magnet and the coil. The coil is generally called as a pickup coil because it is the one which is picking up the EMF. Okay. So let's consolidate the whole story and try to give an explanation. So what is Faraday's law of electromagnetic induction status? If you have a coil and if you have a magnetic source, if the magnetic source is moved towards the coil, if there is a relative motion existing between the magnetic source and the coil, then there is an EMF induced in the coil. So please make a note of it. So write down the heading as Faraday's law of electromagnetic induction and write down the statement for it. When there is a relative motion, existing between, the magnetic source. So here I am very careful about my statement. I am using magnetic source. What do I mean by that? It is not necessary that it is always a permanent magnet. It can be a temporary magnet also. So I repeat the statement. What did I say? When there is a relative motion between the magnetic source and the coil, what is the coil called as? We call it as pickup coil. The bracket you can write it as pickup coil. When there is a relative motion existing between the magnetic source and the pickup coil, comma, there is a change in flux. There is a change in flux taking place. There is a change in flux taking place within the coil, which in turn induces EMF, which in turn induces EMF. That is the electromotive force. Okay. So what we can conclude from here is the EMF which is getting induced is observed to be directly proportional to the rate of change of flux. So d phi by dt. Is it clear? And when you remove the proportionality symbol, it is written as, okay, one more point. EMF is also observed to be proportional to the number of turns present in the point. It is proportional to one thing. What is the rate of change of flux? It is also proportional to the number of turns that the coil has. Then EMF is observed to be directly proportional to n into d phi by dt. Is that clear? Now, when you remove the proportionality symbol, you can write EMF is equal to minus of n into d phi by dt, where the negative sign indicates it is from the significance of Lenz's law. It is from the significance of a law called as Lenz's law, about which I'll explain later. So EMF is equal to negative of n into d phi divided by dt. Is the point here? Is there any doubt in this place? Here?
No doubt, sir.
Okay. Now, if you see, what will be the other unit for EMF that is possible? EMF is equal to minus doesn't have an unit. N doesn't have a unit. What about d phi? Weber by time is measured in second. So Weber per second can also be another unit for EMF in this case. That is volt. N is number of turns directly proportional to n, where the n represents the number of turns. Is it clear to this step? So d phi by dt is what? Rate of change of what flux? We need to be very careful about it, because change in electric flux cannot induce EMF. Only change in magnetic flux can induce EMF. So clear? Now, let us try out a problem from textbook. Just give me a minute. Let us try out an example 6.2. There is a square loop of side 10 centimeters, and it has a resistance of 0.5 ohm. It is placed vertically in the east-west plane. It is placed vertically in the east-west plane. There is a uniform magnetic field of 0.1 Tesla, which is set up across the plane in the northeast direction. Okay. The magnetic field is decreased to 0 in 0.7 seconds at a steady rate. Determine the magnitudes of induced EMF and current during this time interval. So first you need to understand the question. Okay. If I take this as the axis, north, south, east and west. So how is it placed? A square loop of side 10 centimeter and resistance 0.5 ohm is placed vertically in the east-west plane. Means it is placed like this. It is placed vertically in the east-west plane. And how is the magnetic field? It is in the northeast direction. Okay. When it is in the northeast direction, then what is going to be the angle between the magnetic field and the area? It should be 45. It will be 45 degrees. Now, what has happened is The magnetic field initially had a magnitude of 0.1 Tesla, but gradually it got decreased to how much value? 0.1 got decreased to 0 in 0.7 seconds. Less than a second actually. Okay, this happened at a steady rate. Now you need to find the induced EMF. So how do we do that? When they say square loop, loop means one term. Coil means n terms. So EMF is equal to minus of n into, if I write d phi by dt, it is for instantaneous value. Then for average value, what will you get? You will get delta phi divided by delta t. Can I write it like this? Right. They told clearly find the magnitude, so we don't need the minus sign. So EMF will be equal to magnitude of n into delta phi divided by delta t, where n is equal to 1. What about delta phi? Delta phi is final value of flux minus initial value of flux divided by final time minus initial time. So what is the final flux that is taking place? Final flux is 0 because B final into A final into cos of the angle between them minus, what is the initial flux? B initial into A initial into cos of the angle between them divided by final minus initial, which is going to give us 0.7. So B final is 0. What about B initial? B initial is 0.1. So it is 0.1 into, what is the area? 10 square into 10 power minus 4 into cos of 45 degrees, the whole divided by 0.7. Remember, cos 45 is 1 by root 2, right? 1 by root 2 is approximated to 0.7. That is why they give 0.7 in this problem. So cos 45 and 0.7 will get cancelled. So this will be equal to 10 power minus 1 into 10 square into 10 power minus 4. So this will be equal to 10 square into 10 power minus 5. That will be 10 power minus 3. So 10 power minus 3 volt will be the answer. Okay, 10 power minus 3 volt will be what? Will be the EMF induced. If you know the EMF, how will you find the induced current? I is equal to E by R, where R is the resistance. You know E is 10 power minus 3 volt. R is given now, how much is it? 0.5. So divide both, you will get the required answer. Please copy it. If there is any doubt, ask me. Yeah. So if they use hyphenated directions, remember 45, northeast, northwest, 11:40. Is it clear? Yes. So 10 power minus 3 volt, we can also write it as 1 millivolt. Right. Can you guys try the 6.31 without looking at the solution? So try it. Read the question carefully. Use the word circular coil. So when they say coil, number of turns should be Root is number of turns, 1 mark. Coil again, it is more than 1. Coil is more than 1. That's why you see the question clearly says the coil of radius 10 centimeter is 500 turns. Whereas the previous problem they use the word loop. So number of turns is 1. So there is a circular coil of radius 10 centimeter. Okay. So why did they give you radius? You can find the area. Number of turns is 500. Resistance is 2 ohm. This place and it's plane perpendicular to the horizontal component of Earth's magnetic field. Let us assume that there is something called as magnetic field existing. It is rotated about its vertical diameter through 180 degrees in 0.25 seconds. See, that is the most important point. If you are able to identify how that particular coil is placed with respect to magnetic field, half of the problem is solved. So if this is a circular coil, it's rectangular, let's assume it is a circular coil. Okay. And the circular coil is placed, the plane of the circular coil. So this is the plane. So plane of the circular coil is placed perpendicular to the magnetic field. So when the plane of the coil is perpendicular to magnetic field, aerial vector is parallel to magnetic field. Think about it. Makes sense? So this plane is perpendicular to the magnetic field. It is rotated about its vertical diameter through an angle of 180 degrees. Means if initially the area of this coil was in this direction, because when you take the coil, a two-dimensional shape, the aerial vector can be taken in any direction. If you take this area to be the reference with respect to magnetic field, then when you rotate it to 180 degrees, how much has the area rotated? Area also has rotated to an angle of 180, meaning in the first case, if this was the direction of magnetic field, this was the direction of aerial vector also. Whereas once it has got rotated to 180 degrees about its diameter, so when it has got rotated to 180 degrees about its diameter, magnetic field is still in this direction, but the aerial vector is in this direction. So initially it was 0 degrees, finally it is 180 degrees. Initially, if you can take it any way. That is why the question is very clear. They will use the word magnetic. It is up to you. It is up to you. Okay. So if you take initially to be in the direction of magnetic field, finally it will be in the direction opposite to magnetic field, or you can consider vice versa. Is that point clear? Can you try? So I'll tell you the steps. Listen to this carefully. You need not break your head on how to solve these problems. Very simple. The data that you need is always write any problem in science. This is what you need to do. First, write down what they are asking. So EMF is what they are asking is equal to, you write down the formula N into delta phi divided by delta T. So for me to find the magnitude of EMF, what are all the values that I need to approach? First, I need to know the number of turns. 1 minute, charge from here. 9%. Assuming it comes for 20 more minutes, let's see. So the number of turns is given, and you need the change in flux taking place. So change in flux is always final minus initial, and you need the time across which it has taken place. Now collect the data from the question. Look at your textbook. So what have they given? The radius is given as, so radius use small r. So radius is given as 10 centimeter. So 10 into 10 power minus 2 meter. Can I write it like that? Okay. What about magnetic field? So initial magnetic field and final magnetic field are the same only. Because magnetic field's magnitude is not changed. Read the question carefully. Okay. They didn't change the direction of Earth's magnetic field. What is the value? 3 into 10 power minus 5 Tesla. So 3 into 10 power minus 5 Tesla. Initial, theta initial, if you take it as 0 degrees, then what will be the value of theta final? 180 degrees. Then from here, if I find the area final and area initial are the same. And how much are they? It is pi into r square. So this is pi into 10 power minus 1 the whole square, or 10 power minus 2 times pi. Is that right? So these many meters square is the area. What is the amount of time it is taken for this rotation? It is 0.25 seconds, 1/4 of a second. So time or delta t is equal to 0.25 seconds or 1/4 of a second. Take all these values and substitute. So EMF will be equal to N is how much? 500 into final value is B final into A final minus B final into A final into cos. I took it as 180. No, we'll go with that. 180 minus B initial into A initial into cos 0 degrees. The whole divided by time is 1/4. So 500 into B final is how much? Oh, same, no. So 500 into, what can I take out common? 3 into 10 power 5 into area also can be taken out common. Then what is left out inside? 180 minus cos 180 minus cos 0 degrees divided by 1/4. So cos 180 is -1, cos 0 is 1. So -1 is -2. So this whole thing I can write it as 2 in terms of magnitude. So what will I get? 500 into 2. So 1000 into 12 into 10 power 5 into 10 power minus 2 into pi. So 1000. 12 pi, no? 10 power 6, sir. Oh. Then how much is answer? Because 10 power 6 is a very high value. 10 power minus. So 12 pi into 10 power minus 4 Tesla is the answer. Just a minute. Am I clear with this? Oh, sorry. Magnetic. I found EMF. No, it is in terms of volt. Now, what are they asking? The next part is you need to find the induced current. Is it right? So, what is the value of induced current? It will be E divided by R. So, what is E? 12 pi into 10 power minus 4 divided by resistance is how much? So, it will be 6 pi into 10 power minus 4 ampere. Is this right? Are you able to understand this? Right? So, next question that we need to ask is, this is the way problems will be asked. I hope it is easy on Faraday's law. Right. So, in Faraday's law, if you see these two questions, we were only concerned about the magnitude of EMF and the current. Now, the important question is, why did we put the minus sign in the first place? I indicate something I told you, something called as Lenz's law. So we need to understand what exactly that Lenz's law means. Further, we have no other option other than going to the simulation and checking the problems. Now see, the previous case when I showed you the same situation, I asked you to check what is happening when the magnet was moved. Now I'm asking you to check the direction in which the electrons are moving. Okay, constant. When I move the north pole closer to the pickup coil, look at the direction of electrons. Which direction will they move? So when you see from there, they move in downward or upward direction. They move in the downward direction. So when you see from this side, right, it will be like anti-clockwise. Right, that is when you see it from the other side of magnet. This is the coil, this side is magnet. When you see from this side, you will find that the current was in the anti-clockwise direction. Now, what did you do by moving the magnet? Did you increase the flux or decrease the flux? So have these 2 points in your mind. Now I'm taking the same magnet, concentrate. There is some lag happening. Concentrate. If I move this magnet away from the north pole, what happens? The electrons start. So when I move the, so what I do is I move it faster. Observe. Will you observe? Electrons move in the downward direction. When I move it away, it started moving exactly the opposite direction. Bulb going is common. EMF getting increased is common because flux is changing. But how is the flux change creating the EMF is the important question we need to answer. So when I move this coil, the electrons started moving in anti-clockwise when I saw from the other side. Means what is the direction of current? This clockwise. Because electrons and current are always in opposite direction. When I move the north pole away, then what was the direction of current from this side? And the direction of current was in anti-clockwise direction. Now, having all these points connected, I want you to recollect something called as clock rule. If you discuss about this clock rule in the previous chapter. So this point is clear, right? How I can switch the screens. So since you are clear with this point, what I'm going to do now is I'm going to recollect the concept of clock rule. Is that registered in your mind in which direction electrons are moving? Let's see. If I take a circular coil, so in the previous case, the simulation also I showed you a circular coil, but the circular coil was from the side angle. Now, if I take this to be the circular coil, let us say the current is flowing in the clockwise direction. Then what pole gets generated? So just like this, you have this. So a south pole gets generated. Similarly, if the current is flowing in the anti-clockwise direction, then what pole gets generated? So you get a north pole. Now, having all these points in mind, let's see. In the first case, when you move the magnet closer to the pickup coil, right? So remember it like this: coil, left hand side is my magnet with respect to me. So okay, I'll come with respect to you. This side is coil, this side was the magnet. So this is north pole, this south pole, north, south. So when you move the north pole closer, what happened? So when you saw from this side, the electrons started moving in the downward, that is anti-clockwise, and the current was in the clockwise direction. So clockwise means when I see it from this side, when you see it from this side, that is the other side of the magnet. Magnet is here. When you see from this side, when the current is the clockwise direction this side, what pole is getting generated here? South. Then what is the pole on the other side? If this side is south pole, the space which is the side which is facing the magnet should have a north pole. What was the pole you moved closer to the magnet? North. And what was the pole that got generated? So when you moved it away, when you moved the magnet away, what happened to the electrons? They started moving in the clockwise direction, and the current started moving in the anti-clockwise. So what pole got generated on the other side? South. No, this side, north, and this side was south. So when the south pole got generated here, what did you do to the magnet? Did you move it away or did you move it close? You moved it away. Right? So when you moved the north pole closer to the magnet, so closer to the coil, north pole got generated. When you move the north pole away from the coil, south pole got generated. Means the the coil is behaving in such a way that it is always trying to repel the magnet or attract the magnet. So when north pole got generated, what happened? It is trying to repel the magnet. When south pole got generated, it is trying to attract the magnet. So it says that whatever the way you are trying to create the change in flux, the magnet will behave exactly in the opposite way. The pickup coil will exactly behave in the opposite way. Means if you try to always oppose the cause. To put it in simplest terms, when you move the same pole, when you move the north pole, same pole got generated. When you move the pole away from it, the opposite pole got generated. Means when you are trying to increase the flux, the coil is trying to decrease the flux. When you try to decrease the flux, the coil is trying to increase the flux. Means it is exactly trying to do the opposite of whatever you wanted to try. So, and that is what is called as lens. Just give me a minute, I need to charge the laptop. The charger switched off, will display. Okay. Not sure how much charge is there. 5%. Okay, right. So write down the statement for that. It states that the EMF will get induced in a coil. It states that EMF will get induced in a coil in such a way. EMF will get induced in a coil in such a way that it always tries to, in such a way that it always tries to oppose the cause. It always tries to oppose the cause.
Sir, can you repeat it once again?
EMF will get induced in such a way that it will always try to oppose the cause. So below that, write it down in simple terms. If we try to increase the magnetic flux, then the same pole will get generated. Whereas, if we try to decrease the flux, opposite pole gets generated. Is it clear? Okay. Now see, the questions will be on this one. Example 6.4. So in the figure 6.7, you have planar loops. Loops are again one term of different shapes, moving out of or into a region of magnetic field which is directed normal to the plane of away from you. Right? Now determine the direction of induced current in each loop using Lenz's law. Okay. In the first case, if you observe, the coil is there, it is trying to enter into a magnetic field. When it is entering, is there an increase in flux taking place or decrease in flux taking place? So in this case, there is an increase in flux taking place. So when there is an increase in flux taking place, I told you what pole gets generated. Same pole. Now you need to ask a question. Okay. So this board, you have an into mark. So who's receiving the magnetic field line? Is the board receiving the magnetic field line or you are receiving? You are the one who's facing the board. You are emitting the field lines and the board is receiving the field lines. So board is acting like south pole and you are acting like north pole. So when there is an increase in flux, the coil is facing you. What pole are you? North. So what should get generated? North. Whatever you are, the same pole will get generated. If there is an increase in flux. So when I say if it is a north pole, then what should be the direction of current? According to this logic, it should be anti-clockwise. So anti-clockwise means the direction of current is BCDAD. I have only 3% charge. With this problem, let's stop. Okay. So is this point clear? BCDAB. What? So always you should think like what pole you are and what pole your paper is. Okay. So that is why they gave it clearly in the exam. In the question that the paper is receiving the field lines. In a similar way, if you look at the second one, the triangle is moving out of the magnetic field. So when it is moving out of the magnetic field, there is a flux. There is a decrease in flux taking place. So what pole are you? What pole are you? North. What pole will get generated? South. So south pole means what should be the direction of current? Clockwise. So it is AC B. Similarly, in the third case, you guys said same as the previous one. Because it is moving outside and you are north pole, so south pole will get generated. South pole means clockwise current. So it should be AB, CD, B. The E2 mark is received by the board. Who receives magnetic fields? Who has it? So you are the problem. Is this clear? So this is how you solve problems. And I'm not sure if this is going to run. 3%. I don't think you can't do another problem also. Okay. So tomorrow's class, what we'll do is we'll discuss the remaining parts. Actually, there's a small chapter, maximum 2 to 3 more classes will be done with it. Again, AC is a big chapter. Okay, it takes time. So I hope it was clear, right? Whatever you could learn today is clear. So you'll be able to solve problems, right? There are only 2 laws that we discussed. One is Faraday's law. Faraday's law states what? If there is a change in magnetic flux taking place and EMF is induced, electromotive force is induced. Second law says Lenz's law. What does Lenz's law state? The EMF will be induced in such a way that it will always try to oppose the flux. If you're trying to increase the flux, it will get generated in such a way to try to decrease the flux, and vice versa. So these are the 2 laws, and we have seen certain applications also. Revise this and come. The whole chapter runs only on these 2 concepts. If you understand this, the remaining part is easy. Revise it. Those who are online, guys, any doubt?
No, sir.
Okay, that will wind up. We'll wind up.